so we're going to go ahead and kick this thing off again. So David is coming in to give a presentation around what CERN is doing with ARM64. I think this is probably, for me, one of the most exciting talks that we're going to have. You're going to have different talks throughout the day. Some are from vendors, and then some are from people who are really taking this, what we're doing, and actually implementing it and solving real problems. And so I'm very happy to introduce Dave, and so all you.
Okay. So hi everyone, and I'm working for Fermilab organization here in the US, but fully based at CERN, and I work for CMS Experiment. And there are various people working from Princeton University, Nebraska, and Caltech also on this project. And behind that, you can see CMS Detector. That's a very beautiful scientific research tool. So I'm going to try to give a very quick presentation, top to bottom, about CERN, CMS, computing infrastructure, and then go a bit what we have done for 64-bit ARM. So CERN itself is an infrastructure for doing high-energy physics. So that's particle accelerators, detectors, and all the related AT aspects of that. And if you look at the CERN itself is a very worldwide community. We have 21 member states, and there are more incoming. We have lots of different collaborations with different countries. And CERN itself employs about 2.4 thousand people. But majority of the people coming and working at CERN, and that's more than 10,000 people, that's actually, we are working in different institutions, different universities, and all of them pull in Geneva to do with high energy physics research. For example, our budget is about 1.1 million francs. And as I said, CERN itself is a very global organization. So we have people coming from about 113 different countries. So that's amazing. And very quick about the tools. So the major tools you're going to see on all the news probably is LHC. So that's a particle accelerator, 27 kilometers, 100 meters underground. And there are 4 main experiments. There is CMS, ATLAS, LHCb, and ALICE. And I'm working for CMS. And CMS and ATLAS in particular are the biggest scientific tools of most of these detectors. So it's 100 meters underground, and in those caverns, you're going to find these particular 4 detectors. And there are some statistics about the sizes and the cost and how many countries and institutions are involved here. So for example, if you look at CMS detector, that's 14,000 tons of the hardware. That's twice more than the Eiffel Tower. And that's 100 meters underground and packed in a very small space. And if you look into detectors like ATLAS, that is 25 meters in height. Once you get to a cavern, it's very hard to see a machine from top to bottom. It's a very huge scientific machines. And these machines are not static. We built them, but we're constantly going to have maintenance, and we're constantly going to upgrade them. We just finished our long shutdown, which lasted 18 months, and we're back to business to taking the data for the detectors. And in 2012, you looked at the last 2 years of data we gathered, and CMS and ATLAS delivered all the data we have. And this is a picture from the CMS in particular for the Higgs boson. And people won Nobel Prize in 2012 for that discovery. We finally had a proof that Higgs boson exists. So let's start talking about how do we handle the data and how much we get the data. So we have a big machine at HC. It collides in specific points. And one of that point is the CMS detector. And we have tons of data. If you look at the cabling we have in these detectors, and you have all these strands, more than 20,000 cables, and you try to pull and stretch them, so that's 170 kilometers long, all the cabling we have in the detector. So it's very huge machines. And you get huge amounts of data. So we have custom scientific tool, we have custom silicon chip, we have an FPGAs, and of course, at the top of the surface, we have initial farm to process the raw data, to select the last level to select the interesting data. So most of the data we get from a machine, we drop, and we pick only the interesting data. And that's still a very huge amount of data. So we have full ownership of hardware, we have a single customer, we have high bandwidth interconnects. It depends on various levels, but it varies. And once we have the data we want to actually look and analyze, then we have this, what you call a worldwide LHC computing grid. So all that data flows from all the experiments. It flows to the middle of a CERN where we actually store the data and we do initial reconstructions of the data. But we don't have enough compute power to actually do all the analysis, on that data. So we built this virtual supercomputer to process the data. So we have about 42 countries again and 170 computer centers connected to actually get enough of that compute power to deliver the analysis in a meaningful time. So currently, we are recording more than 15 petabytes a year of data. And I tried to look in the last 2 nights, going through all the CERN archives, trying to figure out how much data we have recorded, how much compute power do we have. So about 2011, our virtual supercomputer was 250,000 x86 cores. That's small to the current probably comparisons to what the Google, Facebook had. And CMS experiment was using from 80 to 100,000 of cores to deliver that Higgs boson pictures, to find the discovery of this. For the Ren 2, we actually tripled the amount of the compute power we have for experiments. So this is the number for experiment. And each experiment required more power. Some doubled it, some tripled it. It depends on the experiment. So we're running in the hundreds of thousands of cores. And I tried to figure out, so how much data do we record? So what is the big data in LHC? So in 2012, if you look all the data that the experiments produced, it is about 200 petabytes of information, both simulated and raw data. And I looked at the CMS, in particular CMS experiment, for this year, how much of storage do we have? And if you combine tape and the hard drives, we have 170 petabytes for a single experiment. And for the next year, we have 200 petabytes of information. And that's partially the problem we have. So the problem we have is that we managed to do the first run of all the detectors in LHC. We managed to find the Higgs boson and say it does exist. But we're still going to run for the next 15 years. And for example, CMS expects 2 to 3 orders of magnitude more data coming from all these machines. So we have more power for the Ren 2. That's for the next 2 to 3 years of running. But after that, we have to change something. We have to look into different hardware, have different algorithms to figure out how we can continuously still process huge amounts of data. So I wanted to give a picture of how that grid looks like. So there's no common submission system. So all of these sites independent, we do not own them. So there's IBM LSF, it could be HC Condor, it could be Slurm, it could be whatever. Same applies for the storage. For example, Hadoop is very popular in the US. But if you're a smaller site, you can go for GlusterFS or OneFS. And I tried to do analysis at the beginning of this year to figure out what kind of CPUs we're using. And what we found that we have about 10 years worth of CPUs. And most of that is about 4 or 5 years old. And it's constantly growing. So it's not static that we have this computer grid. We're constantly adding more and more and constantly buying new hardware. So it's always changing every day. So one thing that we had in common is that we're running Red Hat Enterprise Linux-based operating system. It could be Scientific Linux, which is developed by CERN and Fermilab, for example. It could be also CentOS. So currently, everything runs on Scientific Linux, and for the next generation operating system in the grid, CERN selected that to be CentOS 7. So we're not going to be using Scientific Linux. We're going more to a community that's going to have a special interest group to do that. And to distribute the software, CERN decided to build what we call a CERN VM file system. So that's a distributed file system to just deliver the software to all these compute sites, to every node. So we install centrally, and it's available everywhere in the grid, so we can run the data for new software. And so when you have so many compute power, so you have a big problem because it's hard to track how much cores do you have, how much compute power do you have. So at some point, the people came in and decided to make a benchmark, which we call the HEPSpec 2006. So that's a benchmark we're using to do the accounting in LLCG. And you're not talking about the cores. We're talking about the HEPS score 2006 number, which is what we call the power of the compute. We needed some kind of benchmark to tell how much power do you have for the compute. And it's basically a CPU spec 2006 and running all the C++ benchmarks on all the possible cores at the same time on the machine. And you combine that to get a score, and that score means how much power the machine has. So if you look at CMS software, it's complicated. So we have what I want to call a CMS Software Bundle, which is about 200 plus RPMs, which is managed by our experiment. And the top part of that ECMS is double, and that's the actual application. That's an application we use to take the raw data, do all the pattern recognitions, do the analysis and data and everything. And that again consists of 1,200 packages. And that's something like 6 million lines of code developed under 10 years. So we are almost of the size of a Firefox, but there are multiple layers where we have more HEP software, specifically for high-energy physics experiments. We have more standard packages, and we have also the tool chain. So more or less, we pack everything that we need. And if you look what we have a GCC, we have binutils, we have Clang, we have Python, we have OpenSSL, we even have a glibc. We more or less ship almost like a Linux container or software collection, which is fully managed by us. And if you look specifically at the HEP projects, also developed at CERN, for example, Root 6, that's another 1.7 millions of line. Gen 4 for doing simulation, that's another millions of line. So if you try to combine that, you're going to figure out that our code base is very big. And most of that is written in C++ 14 at this point. There's still Python, there's still Fortran, and there's still some C. So we have a very huge software stack. So why we decided to look into new architectures? As I mentioned before, we built double LCG, that's LHC computing grid, based on the fact that commodity just won the war. So we had 32-bit Intel CPUs, and we had Linux, and that worked everywhere. So that was part of the decision to build an infrastructure where you build once and you can run everywhere. And basically, at this point, we have just two silicon vendors dominating, Intel and AMD. And of course, Intel is the dominating silicon vendor at this point. I think for CMS, 75 or 80% of all the cores we have is Intel. But they still have limits. If you look at the next generation big data challenge for LHC experiments, if we're going to continue the way we do now, we would need to buy a lot more cores, build a lot more computer centers to still process the data. So we have to look into different ways. We look at different algorithms again. We look into running GPUs. We look into running Xeon Phis. We also look into running this lightweight, generally proposed, but high-density system. So how do you pack a lot more compute power into the racks to provide you more events per second, and in particular more events per second per watt? So you want to have more performance per watt. The amount we pay for electricity is already huge, and we want to make sure that we can actually lower those costs. So we started to look at the ARM architecture. I mean, at some point, there was a supercomputing conference, and people looking into using the smartphones SoCs to run high-performance computing things. And all experiments, ATLAS, LHCb, and CMS started to do the same thing. And that was about 3 years ago, I believe. So we started to buy this $100 boards to start porting the software. And that worked. I managed to do that. We got some of the things working. Some things didn't work, mainly because we don't have 32-bit software anymore. We never tested anymore. So that was partially an issue. But most of the things did work. And that did solve most of the porting issues to 64-bit ARM also. And we did find some issues and running on Intel architecture. So porting to multiple architectures is very beneficial to trying to find those nasty code places. So that's very advisable. And again, trying to build something on those boards is a very slow process. It's not a simulation, but still it's going to take you 12, 20, 30 hours to build your software. It's a huge software stack again. So when we decided to look into 64-bit ARM, that was at the beginning. There was no hardware at that point. I think there did exist some FPGA-based hardware, but I mean, we couldn't get an access to that. So I decided to just go and download ARM Foundation model, and we already had Fedora 19 at that point. So that was the initial point I started to port the software. And that was very painful. It was like 2 weeks to wait for our toolchain to be built. But that was the beginning. And after some time, I think when OpenSUSE guys did the QEMU thing, and there was a user emulation available, that was amazingly a lot more faster. And you already can build the packages and upload, and you prepare your software, at least some initial stack of that. And about 2+ years ago, we started talking to APM. Once the first kernel patches landed for HDN1, I already wrote to APM saying, I'm interested in 64-bit ARM. And finally, we got APM Mustang, and we did most of the porting and actually showing that the software works on APM Mustang. But we wanted to show that that definitely works. And if that works, development boards is not enough. We need a production systems. So we could have went and bought a lot of APM Mustangs as a demonstrator cluster to show that. Or we could have went and bought the only production system available on the market, and that was HP Moonshot and M400. So we have HP Moonshot 15 servers of those running in CERN Open Lab, and we have another 6 running in Princeton University as a demonstrator cluster. We have also APM Mustang and some other hardware, specifically just for CERN, for example. So for ARM 32-bit, so we did only the CMS and ATLAS, only the software which actually processed the data. But for 64-bit demonstrator cluster, we needed a lot more. We needed all that virtual file systems. We needed all the submission systems. We needed everything to work. So that involved a lot more work, additional work. So of our first demonstration, again, our demo cluster was in the Princeton University. Sadly, at that point, it was only an APM Mustang. And we are still working on an HP Moonshot system. So that's going to be a second demonstrator, much more better software levels, QAs, and upstreaming with that. And at that point, we still have to use a 64-bit Intel node as a master one. But that could be changed in the future. And we decided we don't need a local storage, so we only remotely read files and remotely write those files. And just recently, a few months ago actually, we managed to showcase that it did work, full scale, everything. We managed just to make a job on 64-bit Intel platform, send it from CERN to Princeton University, and that landed on 64-bit ARM worker node. It was reading files remotely from tier 2, from CERN, from Europe, and writing those files to Brazilian site, which we later downloaded back. And that was successful. So that's the pictures of the first actually managed to get something working. And that went through full stack. So that means our software did work. That means that LLCG things did work. That means that CMS computing infrastructure worked. And so basically a full stack which you need to push the job through. And that's another picture actually of APM Mustang. That's our worker nodes. And you can see that there are multiple processes running. Maybe you can see, hopefully you can see. Actually running on that. So in that point, that still was based on Fedora 19. And that's a very terrible release to do that. And we are working with the Red Hat. So we got the access to Red Hat Enterprise Linux Server developer preview. And we are moving completely to this operating system for the next demonstrator. And I just got some news that CentOS is working also very nicely. So we're going to also include CentOS for this next demonstrator. So once you prove that software can work, there's still lots of things to do to make sure what we need to upstream, get the repositories, the builds, and everything like that. You need to start looking into numerical comparison. This is physics. That means we have to get very similar or the best exact numbers as we can get on 64-bit Intel platform. If the numbers are completely different, then it doesn't apply for physics. It's just completely not good. So we did what we call a high statistics comparison. So that means lots of events. You spend lots of hours waiting for the results. And then you compare it and see how the things are different. And a lot of physics we do at CERN is looking at these kinds of histograms. So it's not fancy pictures with all the tracks and colors going in. It's looking at the histograms. And these in particular histograms just show the new data, so 64-bit Intel data minus ARM data, and at the bottom, those blue lines is the difference. So that's the difference we get between 64-bit Intel platform and 64-bit ARM platform. And that we found that most of those differences are extremely minimal. Most of those lines actually, all those dots are exactly at 0. There's still a few places where you have to look into, and you spend a lot more time looking at even more histograms, push more data to fully make sure that it's actually valid for the physics. But we've done the initial things. We did the initial validation. Everything seems to work through our software, through LCG infrastructure, CMS computing infrastructure. And that's an amazing thing. And numerical comparison looks very promising. So again, to summarize the things, we successfully showcased a scientific application to crunch LHC data running on 64-bit ARM, and that worked. A lot of things worked, and it looks like extremely promising, and we want to actually push that to the next stage. We still need to know what we have to do on our side, and we can do that, especially as we get more low-cost, decent hardware. But if you are a silicon vendor, if you're a hardware vendor, if you're a software vendor, and you want to make sure that 64-bit ARM platform is useful in scientific applications, please contact us. We are looking into collaborations to see if 64-bit ARM can be pushed to the next level, and in some years to get the production systems and a full-scale cluster running for LEC data. So that's more or less my presentation. I hope I managed to deliver what I wanted to deliver, and I hope you do have questions. I am here till the mid of Saturday, so if you have questions, find me and ask as much as you can. Do you have any questions?
I'm sure we do.
So I'm curious about the differences you saw in the numbers. Can you give a bit more detail about what was causing that? Is it just floating point differences? Or?
So I only looked at it a few times. I didn't have lots of time because I'm now more concerned of trying to upstream everything. Remove it from my laptop, make sure everything is in, all the repositories exist. But recently we had this thing on Fedora 23 that we had lots of CERN developed software breaking. And we spent some time looking into it. And then particular package was HepMC, for example, developed at CERN several years ago. And what we found, so there was one test case failing showing that there is a difference, 3.5 E minus 15. That was a significant difference, for example. And so we looked at the assembly, and 64-bit ARM assembly is amazing. You just can open the thing and start reading, and it's very clear. And what we found was the problem was, for example, that we had the constructor, which just takes 4 simple numbers, and that's actually confolded to a number. And one thing we didn't use on 64-bit Intel processor was FMA instructions. And ARM comes with FMA enabled. And the numbers were slightly off by E minus 15, but that was already breaking the test. So thanks to Andrew Pinsky from Kavim, actually, we fixed that problem. And that's also solved the same problems for Fedora 23 on S390 power systems, and also solved the problems for different packages. So that's at least what we just recently found. But there's still lots of more work to do actually to look into these differences.
Okay, thanks.
Other questions?
A couple of months back, there was a set of benchmark results published by someone in CERN. It was a comparison between H64 platforms and x86-64 in terms of performance per watt. And the results weren't particularly good looking for ARM. Do you know the gentleman who was doing it? And because a couple of people were, I haven't looked at it myself, but a couple of people suggested that the methodology was wrong. But do you know what's going on with it? Have you sort of followed up on it, or? Or is it just one-off paper and nothing is going on anymore?
So we did initial look in XGene-1 in 2004, last year in the September. At that point, we decided to do a silicon-to-silicon comparison. So there is some technique in XGene-1 when you actually can get the power consumption for different domains. And there is a RAPL in Intel CPU. And that's what we used to do that. And we picked what we thought is a perfect representative Intel CPU on a grid. And I think that was from 2012, a Sanderberg Xeon, not the latest and greatest CPU. And we used some of the simulation benchmarks to do. And at that point, it looked extremely promising for the performance per watt. And just recently, we had the same thing done with the real products. So we had an access to some super microsystems, high-density Intel Avaton. We have HP Moonshot with M300s and also HP Moonshot with M400s. That didn't look very good for the ARM. So we did a CMS, the same benchmark on the Moonshot systems, for example. And also CERN Open Lab did the same thing for a different conference. And you more or less get the same results. But M400, if you fill HP Moonshot for M400 and then our software, you more or less get the same performance comparing to M300, but the power consumption on M400 was 3-point-something times higher. But again, this product is not designed for HPC for high energy physics.
So my question was pretty much, was anyone interested? Have you followed it up with someone outside of CERN, just to see whether it can be improved, how can it be improved, et cetera, et cetera?
We are constantly looking at improvements. We want to look into more high-throughput computing, HPC-like clusters. And we want to start looking more into products. Again, that was a silicon comparison because we didn't have any kind of production systems. But at this point, as we move forward, we care about production-level systems. And you want to compare production-level systems because that's what you buy. Then. So hopefully next year we're going to be benchmarking and showing you the numbers exactly about those products currently available in the market, production-ready systems.
So it did not put you off completely. You will be continuing, right?
We're going to continue that.
Cool.
Any other questions? All right. Please. Thank you.